second talk on the comparative geometry for Ricci curvature.
Thank you. Okay. So during the first lecture, I think hopefully we kind of presented the Laplace comparison and proved the Laplace comparison. Hopefully we also showed how that played a fundamental role in studying manifold with Ricci curvature lower bound. Okay. So it's natural we want to extend it to various cases. Actually, I think in Perelman's work about Poincare conjecture, the reduced volume monotonicity, it plays a fundamental role, and that is really can be viewed as a Bishop-Gromov volume comparison to Ricci flow to space-time. So it's also kind of a generalization. He had a heuristic argument about. So you might, you compare what's the model. The model actually is just a flat Euclidean space. So in some sense, the Ricci flow has some kind of Ricci curvature bond automatically in some. So there's a lot of work on that direction. So in this talk, I'll just focus on the extension to Bakry-Emery curvature and comparison. And integral Ricci. Okay, so let's see how. What is, I think actually yesterday from Andrew's talk, he already covered a lot. Okay, so what's this Bakry-Emery Ricci curvature? This is just really the usual, you can think of the Ricci curvature for so-called smooth metric measure space. So we heard yesterday from the talk, we can even talk about a Ricci curvature bond just for metric measure space. But in this talk, I'm going to focus on the easy case. It's still smooth. So you have a Riemannian manifold with a metric, but the volume, the element, the measure could be, it's changed from the standard one. So we always have the Riemannian measure, and that's usually we study. Now, f is function, usually smooth function on the manifold. So this kind of is, we don't change the metric. Same distance, but only the measure is you're considering differently. Okay, so why it's a little bit maybe unusual. So why do we study this kind of space? Well, it's related to the weak sense, this kind of test. And also this, there's lots of reasons. One of the reasons you can think of, this actually occurs as a class, occurs as a collapsed limit of a smooth manifold. Namely, if I take a manifold n-dimensional and I take another any compact another so if let's say it's a compact, and I give a metric G epsilon, which is a warp product metric. Namely, it's G of the manifold plus epsilon e to the negative f over n. F is a function over here of GF. Let's see, maybe it's twice. Yeah, I want square of that. Okay. So this is a so-called warp product metric. So now if I let epsilon goes to 0, okay, in this, well, basically we are shrinking the fiber in the thing. That's epsilon. This is a metric. So originally, well, it's going to be the space. You're going to just see the M surviving, okay? And so I'm going to take so-called a measured Gromov-Hausdorff limit. We already see that it takes a Gromov-Hausdorff limit. But keep track, the measure will go to 0, which is not interesting. So I take the renormalized measure. So I should save some space here. I take the measure here is d volume of G epsilon, but I normalized. Namely, you take the usual measure, you divide the volume of unit ball so that you scale it, so it will not go to 0. And if that takes this case, then the manifold, the measure is exactly the same space. Okay, so while we keep thinking when you take a limit, always the limit may not be smooth, but if you take a nice limit, the limit could be smooth, and that's how it occurs in this case. Okay, I think so. A little bit history about study. I think Lichner was already back in right after Bakry-Gromov proved the splitting theorem. He kind of had studied this already in the infinite case maybe, and also, so from the name Bakry-Emery, they studied from the diffusion process. And this, I think, Wall product, I think I learned from John Lott, I think maybe his viewpoint, taking the Wall product and come in. Okay, so in this case, now let's see in this Wall product, so what's the Ricci curvature? Well, this is a very explicit metric. We can compute the Ricci curvature in the n direction explicitly, right? Whatever the formula we need. If you can use O'Neill's formula, for example. So Ricci curvature under this metric is equal to the, the Ricci of n. Ricci of the metric G epsilon in n direction is equal to the usual Ricci curvature is coming, and because we have warped, so we have a function of f, and minus 1 over n df cross with df. All right. Okay. So that's in the sequence. If you take in the compute the Ricci curvature, and that's what is coming up in this case. Okay. So what is this limit is coming from the sequence. So we want some kind of continuity about the Ricci curvature. Therefore, this motivates us to define the Ricci curvature of the limit space just to be this one. Okay. So therefore, I denote this to be Ricci of f of n. And that's why we call this is the Ricci curvature of the smooth metric measure space. And we call this will be M Bakry-Emery Ricci curvature because you always have a parameter M here in this automatically in this case. In the questions. Okay, so in the from the motivations, looks like n. We want this is related to we want to take the n to be big or equal to 1 because that's from the dimension of f. But once I wrote this down, I can forget about that. We can just take any n. We can take n to be, we can take m actually, once I have the equation, I can n to be any number, even from negative infinity to infinity. Well, I guess it's well defined except n equal to 0, you might complain. Well, when m equal to 0, I'm going to just assume, so here when m equal to 0, I'll take f is constant. And that's the case. So then it will reduce to the usual Ricci curvature we have. So then in this case, it's just the usual Ricci. So m in this case. Okay, so I really get a parameter of the Ricci all the way from negative infinity to positive infinity. And because this effect here, df, this has a definite sign. This has a definite sign, so it's going to be monotone in some mn, right? When m get big. So since I defined m all the way, so let me make this circle. Here is 0, and this is the infinite. And infinite, positive infinite, negative infinite, in here it's the same, right? So it's positive, negative, infinite. And this is plus direction. Go in here, and this is from negative infinity, it's negative in the m is negative here, and is positive here. So from definition, we can see clearly this is as this n getting from here, this one, the condition, so here, this is a monotone. When n getting, this is getting bigger and bigger, right? Your subtraction less and less n getting bigger. As when I said bigger, it's going this direction. Okay, so this is increasing as n goes from, let's say, 0 to positive infinite and negative infinite to 0. And these are identified. So maybe I say this 0 plus, 0 negative in this direction. Okay, so this is getting bigger. That means the condition Ricci of f lower bound. I'll just write out what is lower bound. It's just to say of, let's say, h of g is weaker. Okay, maybe. Okay, so it's a monotone. Here, you know, it's very strong. When you get to infinite, it's getting weaker, and getting negative, it's even weaker in this case. It's a lower bound condition. You're going all the way around. Because when m is negative, this is a really plus, so it's more easy to satisfy. That's all, right? Okay, so it's exactly have this monotone philosophy. So we have whole family of the curvatures in this case. Any questions? So, okay, this is related to yesterday's talk. This is a smooth case. So if I have Ricci f of n, let's say, is greater or equal to 0, that's exactly corresponding to RCD because I put a 0. And the dimension of my space is different from, it's m plus m, really, because my space, look at, it's just from before, it's plus of this. Of course, I guess I'm not sure how to imagine space with negative dimension. Well, that's, you don't have to, but everything, the equation still makes sense, right? Okay. So this is it's really a special case of RCD space with this. Okay, but my dimension is, that's my convention of m plus n. Really, if we look at the total space, it's added together, right? M plus n. Okay, so, well, it occurs naturally, and why this is interesting. There's a lot of reasons related, but I will just focus on what's because we talk about the Einstein equation, all this. So if we look at the quasi-Einstein, or look at the corresponding Einstein equation, I call it a quasi-Einstein because Einstein is already used, right? Quasi-Einstein equation. So I'll just illustrate from this equation why it's kind of interesting. Notice, so we saw before, so we have whole parameter of n. When n equal to 0, it's just the usual Einstein equation. So the metric is Einstein, right? M equal to 0. Now let me say if m is positive integer. Let's say it's here. In the positive integer, well, it's finite. In this case, this equation tells if this is satisfied, that means my manifold warp product with some fiber with a well-chosen Einstein constant, this is Einstein. So basically, it's a warp product Einstein. And that's one of method used physics in law to construct Einstein metric using warp product. Okay, so if I have this, it's equal, then actually the product, well, with a well-chosen warp product metric in this case, then this is just the warping function. Actually, it's. I need to choose a constant, Einstein constant here, compatible, so that is the case. Okay. So this is, again, in some sense, it's Einstein, right? Okay. Now, if I take m to be infinite, positive or negative, and that's just as a gradient Ricci solitone. Okay, so for the infinite, I want to write a notation introduce. So Ricci of f without the infinite, I'll just write. When m infinite, I'll just write without the infinite because it's special. So in that case, this equation, so m is infinite, so it's just gone. We have Ricci of m plus hashing of f equal to lambda g. That is a gradient Ricci solitone. Okay, in this case. So we said, what about n negative? And negative, for some special m numbers, actually, this is related to conformal Einstein. So if for certain m negative numbers, if this equation is satisfied, is corresponding to the manifold with certain conformal factor, it becomes Einstein. So it's all related to that. Okay. So hopefully now we find each case it's interesting. It's related to lots of subjects actually. So I mean, so of course, Perelman's work he already used this kind of. We also sometimes call this space with a weight in this case. Okay. Now with this setup, so now hopefully we have the notation, we have the space. Then the question is, we want to extend the usual geometry topology to this space, right? So extend geometry, topology, and geometry. I guess I should. So the question, he say, what topological and geometry result can be extended for the usual Ricci curvature can be extended to the Ricci F. So we always have the m here in this case. Okay. And a quicker answer in this, I will discuss a little bit more, is actually the answer is depends on the n, we can see. And we can take to three cases. When m is finite, positive finite, and when m is infinite. The answers are different in each. Or when m is negative, but still bigger than, okay, sorry, it's negative, so, but it's bigger than negative m plus 1 in this case. All right, so in this picture, in the circle, basically, yeah, we have three parts. So this is a region, and we have one which is infinite, and we have this all the way to negative. So this part. And the other part here, so far there's no any result, because this is the weakest part in this equation. There's nothing known about this part in this case. So we can say something about in each part in this case. Okay. Now, so how we do it? Well, for manifold with rich bond, we said the Bochner formula, or the last lecture called Bochner identity, is very important. So we can, for the usual Ricci curvature, we said lots of things can be start from the Bochner formula. So the Bochner formula in this case, we recall, let me write it, is the Laplace of the gradient. Since I already use f, so I want to use u here, is hashing of u squared plus gradient which that was the Bochner formula before, very, very useful. Now in this case, so our space, notice that the measure is changed. So, okay. So therefore, in here, the key is the Laplace. But what will be the corresponding for smooth metric measure space? Right. So natural Laplace is actually equal to the 1 minus dot with let's say it's u here, then u, and dot with gradient u. That's the natural Laplace, because this is a self-adjoint with respect to the new measure. So we should consider the new Laplace in this case. Okay, so actually now then it's natural. We should change the Laplace, the Bochner formula, to change the new Laplace. So actually I put in here f, and putting f here, and putting f here. And actually works. You just put f, still true. It's exactly the same thing. So they have a still really nice Bochner formula, actually. Okay? So the thing is, so rich f is the one we said here, right? So infinite in this case. So only thing notice how we use it. For the Hessian term, when we use it, usually we use Cauchy-Schwarz inequality, right? We say this is big or equal to u square over n, and it's a dimension in this case. So notice I did not change anything in this term. So when we use it, this Laplace did not have any f on it, right? Okay. So if only could we change all the Laplace, then it will be everything will be same, exactly same as before. So this does not have the Laplace in here. And that's the case now we want to make a difference in it. So Ricci f, well, by definition from here, is just equal to, when m is infinite, this is a Ricci f. Right? Okay, so we can write that as the finite f plus this term. Okay, so I can write this term to be equal to the Ricci f of m plus 1 over n df df. The last term here. Okay, so that's when, well, m is finite because with m infinite, this term is gone in this case. So I have two positive terms in here, and these are like, sorry, this I need to apply to gradient f, right? So this is really, I haven't applied to the function. It's really the square. This should be applied to gradient f. I don't have space. And this is equal to inner product of gradient f, gradient u square. Once I apply to the vector, because I need to apply this to the vector. So it's a square term, and this is square term. So in here now, when m is finite, is positive finite, let's say. Okay, I can use this simple inequality. I just, one of them is, well, both are positive. This is really always big or equal to, you can add that together, and the bottom add them together. So so what I get after do this is just equal to half of Laplace f gradient u square. And if I use the inequality, is greater or equal to Laplace f of u square over m plus n plus in this case. So when m is finite, now actually we got exactly the same Bochner inequality. You know, here Laplace f, and this, if you want, you have the bound here. Everything is compatible. So only change in here is the dimension. We want to visualize this space. The dimension is a summation m plus m. That's all. Okay. So therefore, of course, we can have the Laplace comparison. Exactly same proof before, like is, so you have the assumption is Ricci is bigger or equal to m minus 1 h, then the Laplace of the distance function is less or equal to the model space. Now the model space, we want to be careful, the dimension is m plus n in this case now, and the Laplace. Okay, I think this is due to Bakry-Chen in the yeah.
You mean the Ricci f is the first line?
Sorry. Oh, yeah. Sorry. FM. Yes. Yeah. Thank you. Right. So this is Bakry-Chen in 2005. Okay. So once you have the Laplace, as we said before, it's almost everything extends directly, right? In the finite case, you can write the corresponding diameter estimate eigenvalue. So I'll just say result. Results extend direct. I'm not sure. Really don't have the time to write it out. Anyway, I just say, not sure. For example, the Bonnet-Meyer theorem also holds the first Liouville eigenvalue, and those are even true for RCD. They already talked about it. So even so. Sorry, the Laplace. Yes. I'm sorry. Yes, thank you. Yes, definitely. Right. Yeah. Okay, so now let me think about m equal to infinite. Okay, so those are really nice. Almost every result you can extend. So in the infinite case, well, let me give you an example. Since we can see that it does not work quite well in the case because this term, well, if we look at the top of inequality, when m is infinite, this nice term is equal to 0 if you look at it. So we cannot use it anymore. So some of the stuff extend, and usually most of stuff does not extend. So actually, we can look at the hyperbolic space and look at the function, which is distance function. Start from a fixed point. Okay. Well, maybe I use x0. So this is just a basic distance function. This function is very convex. The hashing of f is so much convex such that if you add to the Ricci curvature, then we can check that this is actually positive, strictly. So you can actually, add any number you want. So we can see, well, this is hyperbolic space. It's non-compact. So definitely we don't have Bonnet-Meyer theorem. And we don't have splitting theorem. It has lines, but does not split isometrically in this case. So infinite is really, you cannot. So things don't extend. Directly. There are actually still things you can do it. I'm just in general, the most interesting, like volume comparison stuff. So, for example, you can still get, because you still have that nice Bochner inequality, and you can still use it to get, for example, first eigenvalue estimate in the. Okay, so here I want to present still a Laplace comparison in the infinite case. So that's a joint work with Wiley in 2009. So here we do the infinite case. If the Ricci f is bounded from below, then we still have the Laplace comparison. We can write it out. Laplace f is the model space, but you have the actual thing. So this function I introduced before last lecture is a sine function, basically, on the model space. So here's so this is a sine function. It satisfies a ODE SMH equal to x0 with the initial condition equal to 1. Okay, so what actually I was going to present as a proof but if you remember the proof last time we had, how did we prove the Laplace comparison? We look at the difference to the model, and we multiply by Sm squared, right? And you do the Riccati equation, you do the exactly same thing, okay? Only now, the only difference is that this, I think last time we took the derivative. In this case now, the only change is, well, before the f equal to 0, so it's just less or equal to 0. Now the equation you got, if you just put in, you have this extra term. And if you do the integration by part, don't worry here, this is still the usual Laplace, and you can move over, and that's how we got. Okay, so so basically you need a control. This is the extra term. So you need an extra. Example shows you need usually extra assumption. For example, you can add a gradient or f. And one of the corollary we had is we assume if the f is bounded, then you can rewrite just the plug-in is less or equal to the model. The Laplace is m plus 4k. You can put in the bound and incorporate to the model in the dimension case. Okay, so while f is bounded, it's kind of strong condition, but if the manifold.
I'm confused. I thought f was a function on the manifold. What is written in this integral?
It's along a geodesic. It's a distance function. It's along a. So we look at the distance. Sorry, it's I put the. Okay, I did not introduce. I is a distance function. So you integral along the geodesic. Yeah. Right, is the usual case. x0 and x, that's my r. Yeah. Rx equal to distance. So along any minimum geodesic. Right. So. So yeah, if it's uniformly bounded, you can still control. Again, once you have Laplace, you have volume and so on. So you have the topology and the control in the. Okay, so maybe in the. Well, as you can. Okay, the thing is that so there's many versions. So once you have, we said once have the Laplace, you get the, for example, Bochner-Meyer diameter assumptions in this case. And it's just how you control this tone. There's a variance of this. And at least 10 of the Bochner-Meyer theorems use different kind of things. But everything comes from here. You know how you estimate these tones. So very naive. The simplest one, maybe, it's just assume the bound. So we said if this, although looks a strong condition, but when the manifold for the topology, when the manifold is compact, f is a function on the compact manifold, it's automatically bounded. And you can take the universal cover of those as still bounded. So there's still very large class which apply in this case. This condition is automatically satisfied. Okay, so once you have these, I'll say you have volume. Well, the volume of the f, the weighted volume comparison. And other applications. Okay, any questions? Now I want to mention about this m to be negative. I think I don't have too much. So n to be negative, let's see where is here. Well, this is always true, right? This n could be this equality, any positive for here. N could be positive, negative, doesn't matter. Okay, the thing is when m is negative, so the inequality I had here, it also works. I assume m is positive. But if you look at it, if m is negative, namely it's negative infinite, but I want to be big than, okay, so this is big than negative n. Oh, smaller, sorry. M is smaller than negative and big than negative infinite. Okay. If this m is actually smaller than negative n, I think I'm one more off. Where is the circle? The circle is here. So if I have the negative n, Negative m minus 1 plus 1 is over here. All right. Okay, if we have this negative m, actually this still holds. The only thing is that notice that this will be negative because this is more negative than that. Okay, so still good. This still hold. This inequality I had, still okay. The only thing you come out, this is a negative term. So you have this is negative, okay? But you still have this term in the, and that allows you to do also some work on this case. And for a little bit more, you want to go from m to the negative m plus 1, especially in this case. Okay, actually, I want to say in the RCD, we said we can define electric curvature low bound. In yesterday's talk, like the convexity or of the entropy, you can also do that for m negative, just assume that. And you can do things for all the way to negative m plus 1, but never equal. So in the case when m equal to negative m plus 1, actually the only result I say is a very recent one, is when Will Wiley, when he actually extended this notion of curvature to sectional curvature. And from that work he had, so this is, I will not write it out explicitly, negative m plus 1. Okay, so this is the lowest. Wiley, he had this modified Bochner formula. In this case, he kind of got some kind of, and okay, so once we have that, you know, when f is bounded, you can see, you can do the splitting theorem. Not only just actually only f upper bound is enough if you look at it carefully in this case. And that's, so you also can extend that to the negative case. We have the infinite, you can also do all the way here. But when to the negative m plus 1, amazingly, you also get a splitting, but it's not isometric splitting, it's a warp product splitting. So he proved this by getting a modified Bochner formula. I will not, for the time, I want to cover the integral curvature, so I will not write it out. I can show you what it is. Any questions so far? Okay, so maybe I planned a little bit too much. Now I want to work on actually integral curvature. So this is, but okay, so this is Bakry-Emery is really, you know, you can think of the baby case for RCD because you can check everything here first to see if it's true, then you can extend it. And some of them you can do it directly. So I want to say integral Ricci. So, okay, I'm going to introduce a direct notation directly to state the result. I need to introduce a notation.
Sorry, can I ask a question about this?
Yeah.
I'm sort of getting confused. I remember yesterday Andrea mentioned the splitting result that if you have a negative RCD 0n condition, then you have a Bakry-Émery almost splitting.
It's always, no, always positive. And has to be finite positive. Nothing can be done.
Yes, but okay, but you gave an example to us of over there.
That's n infinite, right?
Was it infinite here? No. There was an example of parabolic space.
Yeah, that's n infinite.
Infinite, okay.
Right. So infinite, yeah, it does not extend. Yeah. So many, as he said, for m finite positive, you can even not just for smooth, you can do RCD, even more general, right? But infinite, you need, I don't know what's, like here, I have assumption on f. I don't know what's that corresponding assumption in RCD, so I don't know what should be the statement. There's no, because this is more special, so we can say more about it. So in general, when m infinite, you cannot, there's no splitting, no volume comparison, but this do have some result. Okay, maybe we can show. Okay. Basically, if your original proof does not use that Hessian term sometimes, then you can extend to infinite because you have still the same inequality. Okay. Yeah, that's a good comment to clarify. Right, okay. Oh, there's no F, of course. I'm getting confused. Okay, for integral, okay, so I'm going to introduce notation is, what is that? Is, okay, we still have the usual lower bound. Okay, well, we always compare to the model. I mean, so I want to look at the Ricci curvature, the smallest, actually, minus rho x. This is the smallest eigenvalue of Ricci. Okay. And I take the positive part. This is a measure how much is the Ricci curvature lies below. So it's m minus 1h. And the rho is the smallest eigenvalue in this case. So we only look at this is a 0, becomes 0. And this is the part which is below 0, below the threshold. You put a threshold. This measures amount of Ricci below m. Okay, so the whole point here in this case, I'm not going to assume any Ricci curvature lower bound in this case. So I just have this quantity, and I'm going to take this quantity and take the p norm which is just equal to the integral. I will do it localized because the manifold may not be compact, so I will do it on the ball. Supremo of x on the ball of bx m of this integral. P and 1 over p in this case. Okay. And, so this measures the Ricci curvature below the threshold in LP sense. So that's what the integral come in, okay, in this case. So now let me also introduce another notation which measures the difference of the Laplace comparison. So there's no F. And I'm taking the positive part. Questions? Oh, yeah. Very good. Exactly. Thanks. Right. Yeah. When R is big, the manifold is finite, then it becomes the whole manifold. Yes, exactly. Okay, so this measures how much Laplace comparison failed. Right. Okay, because before we say this is always less or equal to model, so it's always negative. If I take the positive part, then it's always 0. So now if I using that notation, okay, well, maybe I should say, okay, under this new notation, what we have is the Ricci curvature lower bound becomes just the Ricci pointwise bound is exactly corresponding to this guy equal to 0. And the usual Laplace comparison in this new notation basically saying that if this equal to 0, then the psi is also equal to 0. Right. Okay, so that's reformulate everything now in this new notation in this case. Now, under this new notation, now we can extend the Laplace comparison to to integral curvature. So that's the following result. It's the early work joint with Peter Peterson, myself in 1997. Basically, we say if n-dimensional manifold and P is strictly bigger than n over 2, then we can look at how much the Laplace comparison failed in LP norm. Okay, let's say with the radius r on the ball, it will be always controlled by a constant depends only on MP of how much the Ricci curvature below this threshold felt. And we have 2p norm, it's p norm, so I need to take this to be square root half. And this is also in the same ball, actually, you can take in the. Okay. In here, you want, when h is positive, I need to make a small restriction. I don't want the radius to be too big, to be pi over 2 square root of h. In the, okay, in this, usually it's one of these. Okay. In the proof, so this exactly will extend the usual Laplace comparison. Basically, say if this equals 0, then that's equal to 0, right? Okay. In the p, so how much Laplace comparison felt exactly controlled by how much the Ricci curvature by 0 felt. Okay. Once you have this, you can get again volume comparison. We can extend it to integral curvature and some volume W. In here, notice we don't have any assumption about the Ricci curvature. It's always true. So you can extend some volume comparison similarly like that. You can control the volume by the how much is this. As long as this integral exists, the volume is bounded in this case. So maybe about the condition, the p less or equal to n over 2, the result is not true. So this is, so it's essential that basically, if you look at proof, this constant will be blow up in this case. Okay, so you can do this. I'll not write out the volume comparison somehow. Actually, it's quite. It means you can get, once you have Laplace, intuitively you can get the volume, but it takes some work in this case because the equation is kind of somewhat complicated. Not sure. Maybe I have time to write just to indicate what it looked like. So the volume comparison is you have the one compared to the model. In the model case, we don't care about the point, so I just about the radius of 1 over 2p minus xr of x just r of 1 over 2p is less or equal to a constant. In this case, it's going to depend on p and h and r and the Ricci of p 1/2 in this case. Okay, so it's more. Here is universal constant, but when you do integrate, you have this come in. And this can be more when h equal to 0. This you can write as just a constant times r to the, I think, 1 over n over 2p. So it's more explicit when h equal to 0, everything is. So before you have this is less or equal to 0, and then you have. So if we have let r going to 0 as before, this become 1, you get absolute volume comparison for any, as long as this is bounded and this is bounded. Okay. So it looks like everything can extend, but I want to warn you, in that application, when you do is lots of time, you want the volume doubling, namely the big ball compared with the small ball you want to control. And when you do the cross product, you will see it only works when certain quantity is actually small over here in this case. So for the cross product. So actually, there's nothing, you can do everything actually with sectional curvature. I took here the smallest argument of Ricci. You can define everything for sectional curvature and so on. And we can usually, so for, I'll just say, so for applications, so need a quantity, I'll just write out. Usually after you cross up product, it becomes normalized. P of xr of p 1 over p. Actually, I'll just take the r to be 1. Usually, you need this to be small. Okay. There's lots of counterexamples. If you just bound it, the volume is bounded, but you have no volume doubling if without the smallness. So, okay. So, no volume doubling. without smallness. Okay. Okay, so I just say for sectional curvature, we can also do it. So for example, we can extend as a Grove-Peterson's finite theorem to integral curvature. But lots of times, the extension, you really need to reprove everything. I just warn you. For example, our favorite cinch theorem, for example, the sectional curvature, there's no integral version. You can try to formulate. You say the part below the positive 1 is very small, but there's no cinch theorem. So you really, since it's not automatically, although lots of the results extend in this case. Okay, so that's the Laplace comparison. Now, in the last few minutes, okay, so again, this kind of it's an old result. I want to mention a new result, which is not exactly comparison, but for the integral curvature, hopefully we have lots of applications related to the recent work. So a recent result about integral curvature is actually, we see, I'm going to talk about isoparametric constant, and this is also about the constant. So this is a joint work with Xin Bei and Zhenlei Zhang in this case. So we have a preprint. Let me formulate again. Hopefully you see, usually you need this condition P is strictly bigger than n/2, and you need a smallness condition. Namely, if I will say the integral on a unit ball, let's say for all unit ball of this part, and I'm going to only look at, for the scale thing, I'll look at the when h equal to 0. When h equal to 0, the volume doubling works nice. So I look at the Ricci curvature without h, that means a 0 part, compared to 0 of this 1/p is small than. So when h equal to 0, the smallness only depends on p and n. If h is not equal to 0, the smallness will depend on the r, that's all. So I'm just, it does not too much. So you can do with r too. If you have epsilon, if this epsilon, okay, if that's satisfied, then the isoparametric constant of a ball of radius r, and this r is always less or equal to 1 in this assumption, is actually less or equal to, say, the volume of the ball of xr to the 1/n times a constant depends, which only depends on n and r. Okay, that. Yeah. Okay. So this is just the integral. So I say what's here the definition of isoparametric constant is the supremum of the ratio of the volume of the ball of a domain in the ball of n 1 minus 1/n divided volume of the boundary, in this case, among all the domains which contained in the ball and without touching the boundary. Supremum of all the domains. So this is usually referred to as Dirichlet or local Dirichlet isoparametric constant. Okay, so I don't have to write. I just make some comments about this. So this actually, okay, so when the Ricci curvature bounded below by pointwise, it's very important that this format here, the volume is exactly in this format, actually. The volume and the power is 1/n. I think for pointwise Ricci curvature, actually it's done by Michael Anderson in 1992. And another thing is for integral curvature, some only other versions already know. For example, if you have closed, namely the Newman type, Gallot way back in Gallot is even in 1980, he proves a global one. He already proved the isoparametric constant for integral curvature has this. But for applications, Dean Yang had a version of this. I think he need assumption on the lower volume. Basically, the ball of this, you have to have a volume on a lower bound. Okay, so it looks like I also need a volume lower bound, but in his estimate, it's not explicit. So you need to have a volume, and you have constant. Basically, he has this is M, P, and R. The volume. Okay, so once you have isoparametric constant, this one is then we got a Sobolev, the normalized Sobolev inequality, and you have volume doubling Sobolev. Okay, so many of the results, like the maximal principle, gradient estimate, everything can be extended with some work in this. So actually, another reason we come back to this is recently in the work of Tian and Zhang on the kernel of rich flow, they find a very nice application about the integral curvature. In particularly, based on the early work, they extended the Cheeger coding neighbors result, this the regulated about the limit space, all to integral curvature. But in that work, you need assumption about non-collapsing, because before that is a missing in non-collapsing. But in kernel-rich flow, non-collapsing is automatically satisfied. So it works really wild. So now with this new isoparametric, namely Sobolev constant, we can also extend lots of Cheeger coding neighbors work to collapse the case. Okay, so but since does not work as smoothly, actually we still working. Still one piece is missing to extend fully. We have the L2 hashing estimate, but still we missing part the segment inequality. We have a weaker version. It's not enough to do it. In the non-collapsing case, there's some proof, but it really depends on non-collapsing. So I still have trouble. So, okay, it's almost, that's some motivation for coming back to integral curvature. All right, single eye. Yeah, okay.
Any questions?
Yeah.
Which kind of compactness result one can expect under just a bound on the Ricci over P?
Right. So we, if this is small, right? Exactly. You have the pre-compactness. You can extend it, and the lots of compactness theorem you also extend from the pointwise case. So many results from pointwise can be extended to this one. Yeah. Oh, then there's counterexamples. There's counterexamples.
But one can have, but one can imagine some other convergence where.
No. Okay. So even let's say even I assume the sectional curvature. This counterexample I should. Is let's say even I have so for rich tensor P is bounded. This P is very big. Let's say, and there's a famous Cheeger finite theorem. Let's say. Look at this class. I mean, it's a really very nice condition. There you can have infinite topology. There's no finite at all. So really you cannot talk about convergent theorem most of the time. You really need a smallness condition too. So basically, yeah, without a smallness condition, we still have control on upper bound of the volume. So no volume doubling and no Sobolev, really things can be okay. And the picture of this is you have this dumbbell. You can have this dumbbell to be smaller and smaller as you want, and that's still bounded in this case. So you can have, okay, well, a nice question is about, what kind of singularity. You can control it. So definitely you expect singularities, but maybe so far maybe is it always orbifold, stuff like that. Oh, okay. So think about the questions I should. Yes, one question is you can think about for the Bakry is how much different. We said you last time in Carsten's call, you want to distinguish the class of sectional curvature greater or equal to 0 or non-negative. Here you can ask what's the difference between the usual Ricci curvature and the, so let's see the question. So let's say if n is compact and you have some f such that this is positive, does that imply n has another metric such that the usual is positive? So that's, you know, how do you distinguish the two classes? Maybe topologically they are the same. Of course, there's lots of metric. This, if you take the same metric, it does not have the Ricci, but is there another metric? That's the case. So that's for Bakry. For integral curvature, there are actually lots of questions. You know, you can do the, and okay, I said there's n over, when m equal to n over 2. So most of the time we said it does not work in this case, but let's go back to Gromov's question about if you take just the curvature tensor, take the n over 2, but you know both sides. Here is both sides is different from just the lower bound. If this is sufficiently small, then is the manifold almost flat. In this case, so that's another question. There's lots of other questions, but I think this is one of the really old questions. For n over 2, but you need both sides to be small. Can you say the manifold is actually, namely, have a metric, the pointwise is small. So from integral to pointwise in this case. Sorry. Okay, I think.